Well, thank you everyone for attending today's talk. This will be our last talk of the 2021-2022 seminar series. We'll stop for the summer and then we'll be back for the fall. And today we have Veronica Prush. Dr. Prush is currently a postdoctoral scholar at McGill University. Her research while at McGill has focused on signals of creeping faults in California and the geomorphic record of the faulting in Quebec, which we will be discussing today. She earned her PhD in November of 2020 from the University of California, Davis, and her master's from Cornell University in 2013. This fall, she will join the New Mexico Institute of Mining and Technology as an assistant professor of structural geology. Once again, Dr. Prush, thank you for agreeing on presenting, and stage is yours.
Awesome. Thank you so much. Can you hear me okay?
Yeah, perfect.
Great. Well, thank you everybody for joining the seminar today. And what I'm going to be presenting is preliminary research that our group has been working on to try and tie ongoing seismicity in the Western Quebec seismic zone with the driver of glacial rebound. And so during this talk today, I'm going to start from fairly basic first principles of how we think about hazard and drivers of seismicity in active plate boundary zones, and then tie this to the more complex and enigmatic setting of interplate settings. So I'm going to begin with this map, which is a map of the second invariant of strain as measured by geodetic networks globally. So the second invariant of strain may not be a measurement that you are necessarily familiar with, but the way you can think about this as the strain that causes a change in shape and thereby deformation. So regions on this map that are sort of hot pink or red are locations where we have a lot of relative strain per year, and regions that are in cooler colors tend to have not very much strain per year. So as you probably remember from introductory geology textbooks, what we expect to see is a localization of strain at the margins of plate boundaries. And this is demonstrated quite beautifully when you compare the figure at the upper right of the different plate boundaries in a very simplified sense with the map of the second invariant of strain. So all of this deformation is accommodated at plate boundaries by faults, which are weak zones in the lithosphere. So along these major faults, or along these plate boundary margins, what we find are incredibly beautifully expressed fault zones, such as the San Andreas Fault on the western margin of North America, that we can really come up to and put our hands on and map. And when we think about what these faults are capable of doing, they are locations where we have quasi-periodic release of tectonic strain, and also, of course, a significant source of hazard through the form of earthquakes, as demonstrated beautifully by the San Andreas Fault itself in 1906. So what we want to be able to do at any of these locations is to be able to quantify the amount of seismic hazard that is represented by any of these different fault structures. So how do we measure or quantify earthquake risk? Well, we generally communicate it using measurements and maps such as this, which show peak ground acceleration in units of g-force. So the entire scale shown here is from 0 to 1.5 Gs, and this may not be a measurement that is particularly intuitive to you. So just to put this in perspective that we can all understand, this scale that is shown about 1.5 Gs at a maximum is about half what you experience due to the uninhibited sneeze after sniffing brown pepper. So now we all have a reference frame for understanding G-force. So in order to make a map like this, we really need two basic inputs. We need an understanding of the earthquake source, and we need to understand site response or shaking. So site response is really an engineering measurement. So what we're going to be talking about for most of today is how we understand the earthquake source. So what do we need to know to try and characterize the earthquake source? Well, we need 3 different pieces of information, broadly speaking. We need to know where a fault is located, first of all. We need to know what the maximum or range of possible earthquake magnitudes that fault can produce are. And we need to know how often we should expect an earthquake of any given size to occur. So in locations such as the western margin of North America, where we have these very beautifully expressed fault zones, this is a relatively straightforward process. And we can use paleoseismology principles to try and get this observational data and be able to come up with earthquake magnitude and frequency and try and come up with hazard estimates. But I didn't come here today or enter the Zoom room with all of you to talk to you about the San Andreas Fault. I'm here to talk to you about Quebec. And when we look at Quebec on this map, we see that it actually does have fairly high seismic hazard or peak ground acceleration associated with it. But if we bring back that map of the second invariant of strain that I started this talk with, what we see is that we don't even have it included in this map. We don't even have tectonic strain that we really tend to measure the way we think about it accumulating at plate boundary settings. So why is earthquake hazard so high in Quebec? Well, today what we're going to talk about is I'm going to continue this introductory discussion with a brief comparison of interplate settings and how they really differ in terms of active tectonic principles. I'm going to introduce you to the Western Quebec seismic zone. I'm going to talk to you about how Lidar is really revolutionizing our search for fault scarps in Quebec and beyond. I'm going to show you some examples of possible fault scarps in Quebec. I'm going to finish this talk up by discussing how we can combine numerical models with observational data to test drivers of ongoing seismicity. And I'll tell you now that the driver I'm going to be focusing on for most of the talk, as you can gather from the title of this presentation, is going to be glacial rebound. So interplate settings really do pose substantial challenges to try and understand earthquake hazard. And the primary reason for this is because we can't really rely on tectonic drivers to provide a model like elastic rebound theory to understand how quickly we can expect earthquakes to occur and where we can expect them to occur. We also tend to have very long recurrence intervals between events in these interplate settings. And one of the most intriguing observations that's been proposed in the literature is that there is a chance that these faults don't really rupture twice over thousands of years. And so in the upper part of this figure, I'm showing a modified figure that shows a plate boundary setting where we have displacement across one fault zone, and earthquake timing is shown by these various colored dots just schematically. However, in an interplate setting, what we are seeing are these migrating clusters of seismicity where you have certain faults that will be active at different times as tectonic strain is released. Again, I want to say that this is very, very small amounts of tectonic strain in these sorts of models, but really tectonics is a significant driver. So what this really requires is that we have different models for how fault activity progresses and therefore how we have to envision fault hazard. So with that, let's talk about a very notable interplate setting, which is the Western Quebec seismic zone. So this is a very geologically complex zone, but really the things that you need to know for the purposes of this talk are that we have 1 billion years plus of terrain accretion, which has created various zones such as the Superior Province, the Grenville Province, the St. Lawrence Platform, and the Appalachian Province, where we have very different terrain and very old and very heavily deformed terrain. And that creates very clear lithologic weaknesses in the crust that may possibly be reactivated. So in addition to this accretion, about 600 million years ago, there was an episode of rifting that formed a number of different grabens throughout the province, including the Temiskaming Graben, the Ottawa-Bon Cher Graben, the St. Lawrence Rift Zone, and the Saguenay Graben. So in Quebec, if we remove all of those annotations, what we see are that there is really quite a bit of seismicity in the zone. And we have a history of felt earthquakes. One of the most notable of these is the 1732 magnitude 6 Montreal earthquake, which actually caused damage in the city. In addition to this historical seismicity, we also have quite a bit of secondary evidence for multiple large events throughout the Holocene, including clustered landsliding that might be related to earthquake shaking, and also liquefaction data, especially up in the Charlevoix region, which is more north of the Western Quebec seismic zone. In spite of all this activity, we have a dearth of identified active faults, and in fact, no active surface rupturing fault scarps have been conclusively identified in the Western Quebec seismic zone. In addition to that, the driver seismicity is unclear, as I've mentioned, and a big part of this is that we don't have any active faults that we can try and understand kinematically and in terms of the history of their rupture in order to tie to a model of seismic drivers. So this really leaves us with two major questions, which are, what are the structures that are causing earthquakes, and what mechanism is driving the really concentrated seismicity that we see in southern and eastern Quebec? So let's talk about some of the drivers of seismicity. Well, it's been proposed that pre-existing zones of weakness, primarily the Yaphet and rift structures, are the source faults for all of the seismicity. And there is a pretty good co-location of earthquakes with these Yaphet and rift arms. However, quite a significant amount of seismicity really isn't located on these structures themselves. It's sort of centered in between these major arms of the Yaphet and rifts. So what mechanisms have been invoked to try and understand what's driving the seismicity? Well, one of the primary ones that's been proposed is that thermal weakening of the lithosphere during passing of the Great Meteor hotspot may have caused weakening of the crust. This happened about 120 million years or so ago in Quebec. And it's also been proposed that during the passing of the hotspot tract, that intrusion of mafic bodies has caused crustal strength contrasts, which are now being reactivated by seismicity. It's also been proposed that the high rates of seismicity that we see are due to long aftershock decay times, in particular due to a number of significant 20th century events. However, this mechanism doesn't really explain precisely why these initial events occurred. And then finally, the mechanism I'll be talking about the most today is glacial isostatic adjustment. And at this point in the talk, I just want to describe to you what this means. And it's relatively straightforward from first principles. Basically, what happens is that during glaciation, the weight of the overlying ice sheet actually depresses the crust, and the mantle flows outward underneath the weight of the ice, and the crust begins to sink. After the ice sheet has been removed, flexural rebound drives seismicity as the crust rebounds and the mantle flows basically back into the zone where there was a depression formed in the overlying crust. So fairly straightforward in principle. And we actually have a lot of evidence that Quebec is still uplifting from geodetic data. And in fact, the Western Quebec seismic zone is located in a zone of fairly significant uplift. So a couple of millimeters per year, 4 to 8, depending on which part of the Western Quebec seismic zone you're in. So in spite of all of this, as I mentioned, we have not found any surface rupturing fault scarps yet conclusively. So it does beg the question of where are they? Well, there are similar regions globally that have glacial isostatic adjustment as a potential driving mechanism. I'm going to walk you through how it's been tied as a mechanism to faulting in these regions. And where we're going to focus today is in what's broadly known as Fennoscandia. And in this case, we're going to be looking at examples from Sweden. So there's been significant success in identifying potential post-glacial fault scarps using Lidar in Fennoscandia. And that's basically because there's been a preponderance of available Lidar data to use. And so in this figure on the right, what you're looking at is a map of fault scarps that are indicated by the little red and black lines in the figure. And what in the gray shaded region is showing you in the map of Sweden is the extensive availability of Lidar data. All of that gray zone indicates where there was Lidar available in Sweden as of 2016. And this has really allowed people to identify faults in these zones. Similar work has been done in, for example, in Finland. So you don't necessarily need the Lidar data to find fault scarps in Fennoscandia. And a particularly striking example of a postglacial fault scarp is the Parve fault in northern Sweden. And the Parve fault you can see from the air. And it's indicated here as the very significant scarp located between the two yellow triangles that I've annotated on this figure. And this fault scarp is so impressive that you can in fact land your helicopter on top of it if you so chose. So not all fault scarps are this impressive and this easy to identify in the field. And this is really where Lidar comes in hand. So in this figure, what you're looking at is a very well expressed postglacial fault scarp. It's indicated between the two white arrows. And this is an example from Finland. And really what Lidar allows you to do is to look beneath the dense vegetation cover and be able to identify locations where offset of glacial sediments or postglacial Holocene sediments in this case have been offset, and allow you to find and measure these offsets and locate places where you could actually date timing of fault rupture and come up with a recurrence history of fault activity as you do in more active plate boundary settings. So this methodology is not without its challenges. It's very common in glaciated landscapes to confuse postglacial fault scarps with glacial lineaments in particular. And there's also fairly high erosion rates in these zones. In Quebec in particular, what we run into is fairly dense vegetation cover, which obscures any chance of finding some of these fault scarps unless you happen to stumble across it. And in the case of Quebec, until recently, widespread Lidar coverage was not really available. So we couldn't even begin to make the same sort of regional scale mapping program that has been undertaken in Fennoscandia. However, moving into the methods section of this talk, the Western Quebec seismic zone is now covered by Lidar, which is really revolutionary for trying to find these structures. And the Lidar that's available is quite spectacular. We're able to see very fine features, or perhaps not so fine features, of glacial scouring and lineations. You can actually do some preliminary mapping of the glacial geomorphology and post-glacial geomorphology. And you can identify fractures or potential post-glacial fault scarps. So myself and 3 incredible undergraduate students have been working for about a year plus to try and map remotely some possible post-glacial fault scarps in the Western Quebec seismic zone. And what we focused in on are locations where we know we have historic ruptures, especially during the 20th century, that might be co-located with magnitude 6+ events. And we've also tried to take a look at varying types of terrain in order to see how the appearance of these fault scarps could change as you move across the province. So in particular today, I'm going to highlight for you results from 3 key regions, 3 very exemplary regions of how fault scarps can look throughout the Quebec province. And these are the western edge of the Grenville province, where we see beautifully glacially scoured bedrock. A location within the St. Lawrence platform where we see glacial deposits of Champlain sea sediments that have possibly been offset. And we're also going to look very close to the St. Lawrence rift zone, kind of more towards the Charlevoix seismic zone. So the students that I've been working with and I have developed a set of criteria to categorize our confidence in our interpretations, our preliminary remote sensing observations, and I'll be presenting these to you in the next slide. But I want to point out now, as I'll point out again later in this talk, that we really need to undertake fieldwork to verify our interpretations. It's very hard to be certain that any of the fractures that you're seeing or any of the scarps you're seeing are conclusively post-glacial fault scarps or Pleistocene fault scarps without going out to the field and actually doing pretty substantial work to verify this interpretation. So I'll talk about some of our preliminary work, but I'll say now that a lot of this work is very much still ongoing. So there are 4 criteria that I'll be framing the results section around of this talk. And that is that to identify high confidence fault scarps, what we expect to see are offset, Pleistocene, late Pleistocene sediments and glacial landforms. We expect a fairly low sinuosity, and this is basically so that we make sure we aren't confusing fault scarps with other potential very impressive scarps in this LiDAR imagery, including, for example, terrace edges. And also we're looking for consistency in scarp facing direction and offset. That means that basically if a scarp is facing to the south, then it stays facing to the south along its entire length, and that offset is fairly regular. And we're also looking for a fairly sharp profile of the scarp in topographic data. And that's because it's very common to see fractures in the crust that basically have been enhanced by glacial scouring and freeze thaw as glaciers moved over the landscape. And this is a particularly hard thing to try and untie from remote sensing data alone. But we're going to start by looking, in fact, at this location, which is in very close to Temiskaming, Quebec. So what we're looking at here are a series of scarps in bedrock. And again, this is 15 kilometers northwest of Temiskaming. And as I mentioned earlier, there was a fairly substantial 20th century earthquake here that actually caused damage as much as 300 kilometers away from its epicenter. This was a magnitude 6.1 event, and subsequent field surveys after the rupture did not find any evidence of surface offset. So what we're looking at here are a couple of different, the first 2 indicators are possibly identified from this figure alone. What we see are offset sediments and glacial landforms. I'll zoom in on some of those in the next slide. And we also see fairly low sinuosity. These scarps tend to cut straight across the glacially abraded bedrock. So we're going to zoom into the little black box that just popped up on the screen. And I'm going to show you 2 different topographic profiles that demonstrate what these scarps look like in profile. And I want to point out that those 2 yellow arrows are actually pointing at glacial scour / landforms that have been offset or disturbed by these cracks. So the first topographic profile that just popped up on the screen is a 4-meter scarp located at X to X prime, fairly sharp in profile. And there is a 6-meter scarp at the location of the Y and Y prime indicators that is also fairly sharp in its morphology. And in terms of these 2 scarps, what we see are that the facing direction and offset are fairly consistent along strike. I haven't shown multiple topographic profiles from these scarps in the interest of time, but in addition to consistency in facing direction, we also have fairly sharp scarps in topographic profile. So in this case, our 4 primary fault criteria have been met. There is a caution with this location, which I've sort of alluded to previously, which is that it's possible that these are fracture sets that have been enhanced by glacial plucking and erosion. And so this is a location we have not been able to travel to yet due to basically COVID constraints, but we're hoping to be able to do so in the near future to try and find these scarps and do a more thorough fieldwork undertaking of them. So the next location we're going to go to is very near to Montreal. And this is the location where we're going to be looking at what offset of a potential fault by a potential fault scarp in glacial and Lake Champlain sediments could look like. But first, I want to point out to you just how close the scarp is to the city of Montreal. So this is a basic figure of where in Quebec we're talking about. And if I zoom in to that black box there, this is a Google Earth image where that black box is located. The yellow dots indicate major cities in Quebec, and the scarp is located about 50 kilometers north of the island of Montreal. I want to point out that a lot of the data and field observational workup that's being done at this location is being undertaken by Aube, who is actually in this seminar, I believe still. And so all credit goes to Aube for this work. So let's take a look at what the LiDAR data looks like. First of all, once again, we're seeing offset of sediments and glacial landforms. In particular, we're seeing a series of rib moraines that are heading down towards the south of the figure. And these appear to have been offset by the fault scarp. This fault scarp, again, is showing low sinuosity, which is, again, something that we're looking for as a preliminary sort of indicator of high confidence in this fault scarp. I want to point out that this is a sort of a tricky area to work in from a field data perspective, because there has been fairly substantial anthropogenic modification of the zone. So what I just popped up on the screen here are just a handful of parallel lines that hopefully will draw your eye to just how much irrigation and plowing and farm work has been done in the zone, and has fairly substantially modified the region. However, there's probably been a bit of modification near the scarp, particularly where the black arrow is, but this area is still mostly forested and has not been as disturbed as other locations nearby. So we're going to take a look at a couple of elevation profiles from X to X prime and Y to Y prime. And looking first at the X to X prime profile, what we see, it's a little bit noisier than the previous scarps that I showed you for the Temiskaming region. But we have a fairly well expressed 2.5 meter scarp. And when you visit this location in the field, there's oak for scale. You can see that the scarp, the yellow arrow is pointing to it, hopefully you can see it through the trees, is pretty well expressed. So the second scarp that we're looking at is just a long strike out to the east. And at this location, we once again find a 2.5 meter scarp. Data again, a little bit noisy, but still we can make out the scarp fairly easily. So what we find here is that displacement is consistently about 2.5 meters along strike. So at this location, we've found our 4 indicators that we're hoping to find to have a high confidence remote sensing identification of a possible fault scarp. But we can take this a step further because we've already done some field work at this location. So I'm going to show you some very preliminary GPR data from this location. So I want to point out first that the GPR equipment, ground penetrating radar equipment, was provided very graciously by UCAM, and the faculty there allowed Obe and myself to take this GPR equipment out this year. So in February, we went out to this fault scarp and undertook a GPR field survey. There's Obe again enjoying the chilly Quebec weather. Fortunately, it was a beautiful day, which was a tremendous relief. It could have been very cold. And we chose to do this profiling, do the subsurface measurement in frozen conditions, because in this location, in preliminary pits that we dug in the fall of 2021, we found that the ground is actually fairly wet, and you really want to have as not wet, as dry conditions as possible to try and get good GPR imagery out of a site. So we chose to return in February in order to have frozen conditions that would hopefully lead to better reflectors in our GPR data. So we undertook a 30-meter long survey along the fault scarp. And for those of you who are familiar with ground penetrating radar, we're assuming a velocity conversion of 0.165 meters per nanoseconds, which if you're not familiar with GPR, basically means we're assuming ice or frozen conditions. So here's this preliminary data. This is all work that's been done by Obe. And what we can see here, I'll describe it to you first, and then I'll put a little bit of annotation on the screen to guide your eye, is we see a series of fairly well-expressed dipping reflectors that are moving towards the southern part of the diagram on the right. And out towards the north, we have a bit more chaos in terms of the reflectors. And we've interpreted the chaotic reflectors to indicate possibly unconsolidated sediments, and the stronger reflectors to indicate dipping bedrock. At this location, the bedrock is actually quite shallow. It's only a couple of meters down, and we actually see outcropping bedrock along the scarp. So I've interpreted here a possible normal fault scarp given this relationship, but I want to caution that we're not entirely sure that this is the case. We still have a lot of field work to do. So far we have pretty good evidence that this might actually be a fault scarp. However, as with the other side, we have a couple of things that we need to work out in the field first before we're 100% confident that we found a postglacial fault scarp. First, that co-location with ribbed moraines is actually a little bit disconcerting when you look at the Lidar data, because those ribbed moraines actually have fairly large scarps associated with them, as you can see near the black arrow. However, the scarp that we see offsetting these ribbed moraines is much longer and extends beyond the really well-defined edges of those ribbed moraines. So we feel pretty confident that we're looking at a real structure. This could, however, possibly be a buttress unconformity of some type that has been deposited against by unconsolidated sediments associated with Lake Champlain sea deposition. And all of this will hopefully be revealed by paleoseismic trenching that we're planning on undertaking this fall. So we're now going to move on to the last candidate scarp, and this is the one that's located near the St. Lawrence Rift Zone. And this particular scarp is about 50 kilometers west of the city of Quebec City. So this LiDAR map is actually quite complicated. There's a lot of superficial geology to see here. And so that you can kind of make out the scarp in the LiDAR data, I'm going to drop a quick interpretation of what you're looking at that is derived from the CGO interactive map. And I've redrawn the context a little bit to match what we've seen in the field and also in the remote sensing data. So the broad red band in the center of the figure is Grenville bedrock. And on the western side of the figure, it is mapped as undifferentiated till. We have no reason to believe this isn't the case based on our preliminary field observations. And then the yellow bands, both through sort of the left third of the diagram and then on the southeastern side of the figure, are moraine and Lake Champlain sediments. And as you can see, as I've highlighted for you in the center of those two white circles, there are actually offsets that you can see in the LiDAR data. So we do in fact see offset of sediments and glacial landforms, and again, low sinuosity at this location. So I'm going to zoom in a little bit to this figure and show you what this offset looks like in the field. There's an offset moraine right there. Christy Rose is elongating herself for scale. And one of the challenges I found as somebody who's worked mostly in desert settings in active tectonics so far in my career is that it's quite hard to take convincing field photos in Quebec. And I'm not sure that I've completely sorted that out just yet, but here's a couple of helpful annotations for you. The approximate fault trace is towards the lower part of the picture. It's not very well expressed, and so no worries if you weren't able to see it. And that hill behind Christy that's rising is that moraine that I just highlighted with the red arrow. And this picture is facing in the direction of the yellow arrow. So in order to enhance our ability to see how significant the scarp is, I'm going to draw yet another topographic profile. And in this case, what we're seeing is actually a fairly significant fault scarp. This is a scarp that might be as high as 20 meters. And this time, I'm not really confident enough to say this is in fact a 20-meter scarp. I want to point out that there's fairly serious undercutting of this structure by a more or less east-west flowing drainage that I've highlighted with these blue arrows both in the LiDAR imagery and in the LiDAR profile. You can see the channel in the LiDAR data. So I believe that this feature has been modified and sort of enhanced by erosional processes. But regardless, it's a very sharp feature and it's quite impressive in terms of its size. So we're still working out exactly how much deformation might be associated with the structure, but we can say that the facing direction and offset tend to be fairly consistent along its length, more or less. This is a bit of a complex structure, as I'll show you in a few slides. And we do see a sharp scarp in the topographic profile. So we also have bedrock observations to assist us in our interpretation. And you can see very subtle indications of offset in the bedrock indicated at both the yellow and the red arrows in this figure. And I'm going to show you a picture of what that bedrock fault exposure looks like at the location of the red arrow. That's me for scale, going out in the field again in snowy Quebec. And I'm about 5'5" for reference. So this is a fairly large exposure. And this is a very flat plane, and that's in the bedrock. And the reason that we feel confident saying this is actually a bedrock fault exposure is because we took a sample of it and we sent it out for thin sections. Unfortunately, those thin sections haven't come back yet. We only retrieved the sample in November of last year. But what I can tell you is that in the hand sample, what we see is a set of wispy sort of looking lineaments that look like cataclastic zone. So we feel fairly confident saying that this is a bedrock fault scarp, and whether or not this reactivation that we're seeing in the LiDAR data is in fact Holocene is ongoing work. Again, the cautions with this particular fault scarp are that the displacement in the bedrock is fairly inconsistent. And again, this probably has to do a bit with undercutting by erosion, but you can see that the offset does disappear a bit in the location of the red arrow. And this could be due to erosion by that channel. It's hard to say without further field work, but the trace is not completely continuous. And this is definitely something that we're working on understanding better. However, the fact that it continues beyond this location where it disappears off to the western side of the figure and it's offsetting mapped undifferentiated till does give us confidence that this is in fact a structure. It has a complex history. So these are three of the most promising features among many that we've identified in Quebec. And now I'm going to tell you how we can take these field observations and try and tie it to glacial rebound as a potential driver of ongoing seismicity. So we're looking again at a schematic of how rebound can be used as a driving mechanism for seismicity. And in this case, we're looking at an ice sheet that is again depressing the lithosphere. This entire zone that you're seeing, the broad crustal zone, is the entire lithosphere. And what we're really focused on here is the complexity and variation in imposed stress field that you can experience due to compression by the ice sheet or depression by the ice sheet. And that's that you'll see extension in the peripheral bulge and margins of the ice sheet. And in the central part beneath the ice sheet itself, what you'll see is compressional sort of stress fields. I'm sure some people have been drawn to this in this figure. There is what's known as a neutral plane in the lithosphere where the sense of extension and compression flips. But for the purposes of the talk that I'm giving to all of you today, really what we want to think about is that at the peripheral bulge and near the margin of the ice sheet, we have extension, and beneath the ice sheet, we have compression. When the ice sheet disappears, we see more or less a reversal of these patterns. So how can we model this? Well, we model this using 3D finite element models. And so this portion of the talk is really work that's been undertaken by our collaborators, Rebecca and Holger-Steffen, and I'm presenting it on their behalf. So this finite element model is flat, first of all. It's not spherical, but this is really okay for the dimensions of the problem that we're looking at. And in this flat disk, this finite element model, we have a layered lithosphere and mantle where we have an elastic crust and a viscoelastic mantle underneath it so that you can have flowing of the mantle beneath the ice sheet as it presses down. I want to point out that the variation in rheology of this lithosphere and mantle is vertically varying only. We don't accommodate or allow for any lateral variation in these sorts of models. So what we can do once we build this model of the lithosphere and mantle is we can actually impose a circular ice sheet on top of the crust that can vary in height and width through time. And that ice sheet is indicated by that little bluish circle in the center of the little cube. So we add the imposed stress field due to this ice sheet to an estimate of the background tectonic stress field. And then what we can do is we can use the Coulomb failure stress to test the likelihood of fault rupture at various faults throughout and adjacent to and underneath this circular ice sheet. So I'm shown here, or I'm indicated here on the Stefan's figure, 5 different locations, for example, and you could test changes in stress field, changes in fault kinematics, and how that's likely, and how these faults might be triggered by motion and waxing and waning of the ice sheet. So if the Coulomb failure stress is all Greek to you, then I can promise you that for the last couple of slides of this talk, I'll be guiding your eye using this sort of a diagram. So on the y-axis of this diagram, we have changes in Coulomb failure stress, and on the x-axis, we have time, basically. And all of these figures I'll be indicating when the widespread glacial recession at about 11,000 years occurred with this dashed line. And importantly, I'll be showing you when rupture is favorable for any of the different models that are used. So the 4 lines that are shown on this figure are 4 different parameterizations of ice sheet models. I'm not going to be going into the details of which ice sheet models we're using and why, because that's sort of beyond the scope of the current talk, but know that there are a number of different ice sheets that are, and ice sheets and parameterizations of the lithospheric mantle that are being imposed. So in order to test this as a mechanism for Quebec, what we are using as inputs are location of the faults, their orientation, assumed strike and dip, their kinematics, and what we want to include in the future is rupture history. And this is going to take some geochronology work, which we haven't been able to undertake yet at this time. But in the future, what we're hoping to be able to do is use the timing of fault activity to try and match whether or not favorable rupture periods are consistent with the ice sheet models that we're using. So with that, let's look at some of the preliminary numerical modeling results from this work. And we're going to start by looking at the scarp that's located west of Quebec City. So observationally, what we know is that this scarp is approximately east-west oriented, and it has a fairly high dip, about 76 degrees, dipping to the south, as far as we can tell from the Lidar imagery. This is an oblique dip slip fault, we think, but predominantly dip slip, and that has to do with measurements we've made along strike of the fault. The model makes a couple of important assumptions. The first is that the background stress field that we impose is approximately southeast-northwest directed. The faults in both this and the next test case that I'll be showing you are oriented east-west, which is approximately consistent. And if we're looking at normal and strike slip faults, we're going to be assuming a 75-degree dip. And if we're looking at thrust faults, we're assuming a 30-degree dip. Now, because we haven't trenched these sites and we haven't got our complete sort of model of what these faults kinematics are, and really a good understanding, a rigorous understanding of dip in particular, we're going to be testing all different 3 types of faults: normal, strike slip, and thrust faults. So let's look at the data. What we find is that the timing of activity depends, as is expected, I imagine, on the ice sheet model we're using and the type of fault that we assume is occurring at these locations. So I'm going to guide your eyes here in a moment with some arrows to help you make sense of this. But what you're looking at here are 9 different lines with 3 different colors that correspond to different parameterizations of both the lithospheric mantle and the different GIA models. So there are 2 GIA models in this figure, and one of those models has different lithospheric thicknesses. So the same model with a different lithospheric thickness is indicated by the maroon and sort of tan lines, and then the other ice sheet models indicated by the light blue lines. Normal faults are dotted lines, strike slip faults are solid lines, and thrust faults are dashed lines in this model. Once again, widespread glacial recession occurred at about 11,000 years, and the upper half of the diagram indicates where the red shading is when rupture is favorable through time. So in the first of these models, what we find is that normal or strike slip kinematics is allowable between very precise demarcations of 10 and 16,000 years, or if we assume using this particular GIA model, then this is a thrust fault, then the fault could have been active after 4,000 years. So this is consistent with the way this fault looks geomorphologically. The second model finds that if this is a normal or strike slip fault, It was active between 30 and 50,000 years ago, so probably not consistent given the significant amount of erosion and reworking of the entire surface based after or during glaciation. And if this is a thrust fault in the second model, then it was possibly going to be active in the future, but there isn't really an indication it's been active in the recent past. So for the second location, where we have a scarp that's located north of Montreal, we have a very similar strike, about 264, a little bit less purely east-west, but still fairly east-west in its orientation. And in this case, we believe the fault is dipping north, but we still really want to trench this structure and really get a sense of exactly how it's dipping. In either case, we assume that this is a pure dip slip fault because we don't really see any indicators of obliquity in its motion. Again, just as a reminder, the model assumptions are a background tectonic stress field that's oriented southeast northwest. The fault is embedded as striking more or less purely east-west. And normal and strike slip faults, again, have a 75-degree dip, and thrust faults have a 30-degree dip. So here are the results for this fault. And what we find are that if this is a normal or strike slip fault, one of the models suggests that, again, this was active about 30 to 50,000 years ago, and then it might be active in the future, but has not been active in the recent past. The other model finds that if it's a normal or strike slip fault, the fault has probably been inactive. And so this actually does not agree with my interpretation of the GPR results. So I'm looking forward to trenching the structure. But if it's a thrust fault, what we find is that the fault should be active about 2,000 years ago or less, which is again consistent with what we're seeing in the field. So in conclusion, what I've shown you today and hopefully convinced you of is that interplate settings present unique challenges to seismic hazard assessment and really require a mix of methods to be able to understand exactly why we have high seismicity areas in these interplate settings. And that Quebec itself is a remarkably seismically active area, and the drivers do so remain fairly enigmatic. Testing any given driver of seismicity requires knowledge of fault locations, kinematics, and rupture history for this or any other model. And this newly released Lidar data has really provided us with an unprecedented opportunity to try and identify surface rupturing fault scarps. But I want to underscore that any of our interpretations really require the ongoing field validations using both subsurface geophysical or superficial geophysical methods, using trenching and using other paleoseismic principles in order to convince ourselves that what we're seeing is actually a fault scarp. And finally, what I hope I've convinced you of is that by combining observational data for both remote sensing and fieldwork with numerical models, we've really had this fresh new opportunity to try and understand whether or not glacial rebound is acting as a driver of seismicity in this area. So with that, I'll thank you for your attention, and I'm happy to take any questions.